Graph engineering makes the execution structure around an agent explicit. Here, graph means the control graph that orchestrates work, not a knowledge graph used for retrieval. It defines what can run, what must wait, which state crosses each handoff, who owns each decision, and how failure terminates. I'm Mehrdad. I'll build that architecture from first principles, then compare it fairly with loop engineering. The difference is where control lives, and whether engineers can inspect it. Start with the plain meaning. A graph is an execution model made from capability nodes, decision edges, and shared state. A node may be ordinary code, a tool call, one model call, a complete agent, an evaluator, or a human approval. An edge decides whether another node is eligible to run. State carries the information the next node is allowed to use. Graph engineering is the work of designing those elements as one controllable system. If you value mechanism-first explanations like this, like the video, and subscribe to Multi-Agent Academy. Nodes and arrows are only the visible surface. A production graph also needs gates, joins, checkpoints, and explicit terminal states. A gate blocks progress until a condition holds. A join combines branches without hiding missing work or disagreement. A checkpoint persists the current plan and state, so execution can resume after interruption. A terminal state explains why the run stopped. Completed, timed out, budget exhausted, rejected, and waiting for human input are different outcomes. Using only done throws away operational meaning. Together, these parts turn a diagram into an execution architecture. One useful formal view treats the graph as a scheduler. The system has states, a function that computes which work is ready, a policy that chooses what to dispatch, observations from execution, and a transition function that updates the system. Two properties matter most. Ready-set cardinality says how many work units are eligible now. Policy explicitness says how inspectable the dispatch decision is. This view is useful because it separates topology from execution. Drawing 5 nodes does not create concurrency. The scheduler creates concurrency only when dependencies, resources, and policy make several nodes ready at the same time. Now we can compare without caricaturing the loop. Loop engineering designs one persistent trajectory around a goal. The agent acts, observes the environment, updates external state, checks progress, and continues or stops. A well-engineered loop has tool contracts, a verifier, retry limits, a budget, durable memory, and a clear stopping condition. Its advantage is context integration. One trajectory can preserve the full reasoning history while the useful path emerges. For sequential or exploratory work, that simplicity is often exactly right. A loop becomes fragile only when important dependencies, recovery rules, or approvals remain implicit, and the model must remember them at every turn. In a conventional loop, one work unit is active, and the model usually chooses the next action from inside its trajectory. In an explicit graph, several units may become eligible, and the dispatch policy can live outside the model. That is the clean comparison. One ready unit versus a computed ready set, and implicit model routing versus inspectable system routing. Neither is automatically better. If the task is sequential, a larger ready set adds nothing. If independent work really exists, forcing everything through one trajectory creates avoidable serialization. A graph cannot manufacture parallel work. It can only expose parallelism already present in the task. A dependency written only in the context window is a remembered constraint, not an enforced one. The model may respect it, overlook it, or reinterpret it after the plan changes. In a graph, the dependency becomes an edge in a versioned plan. Before dispatch, the scheduler checks whether predecessor states, required evidence, permissions, and budgets satisfy that edge. This moves control from narrative memory into executable structure. The consequence is important. Invalid ordering becomes preventable before a node runs, rather than discoverable after the model has already acted. A node should be narrow enough to test, retry, replace, and observe independently. Its contract names one objective, accepted inputs, the state update it may produce, tools and permissions it may use, evidence it must attach, and the result it returns on failure. Idempotency belongs in that contract too, because a safe retry for a read may be unsafe for a side-affecting operation. If one node plans, researches, writes, evaluates, and publishes, the box is not modular. It is an opaque loop with a label. Graph reliability begins by making each node deliberately boring. An edge represents a decision, so the architecture must say who owns it. Deterministic code should own machine-verifiable conditions: schema validity, test outcomes, budget limits, permissions, and required artifact presence. A model can own semantic routing when the boundary depends on meaning rather than an exact rule. A human should own irreversible actions, policy exceptions, and changes to the root objective. This division prevents a common design error, using a probabilistic model to rediscover a fact the system already knows. Put judgment only where interpretation is genuinely required. Graph state should be a schema-defined object, not whatever remains in a transcript. It records the objective, plan version, completed nodes, branch outputs, evidence provenance, retries, spend, deadlines, human decisions, errors, and terminal status. Checkpoint that state at meaningful transitions. Then an interrupted run can resume from a known boundary, and a failed node can retry without replaying unrelated work. Durable state also makes long human approvals practical. The process can wait without keeping one model context alive. This is where a graph becomes more than routing. It becomes a resumable execution system. Failure handling needs an algorithm. First, classify the failure and record the evidence. Retry only when the operation is safe and the attempt bound remains. If the node contract or local plan is wrong, patch that local structure. Replan only when the current plan can no longer satisfy the objective. Each escalation should be bounded, versioned, and visible in state. This ordering prevents recovery from becoming another unbounded agent loop. It can guarantee that the scheduler eventually stops under its stated assumptions. It cannot guarantee that the plan or the model output is semantically correct. A perfectly controlled system can still execute the wrong plan. Fan out is easy to draw. Fan in is where the architecture becomes real. Some branches are constructive. Every result is required before execution can continue. Their join must detect missing work, validate each output, preserve provenance, and define timeout behavior. Other branches represent alternatives, where one acceptable result may be enough. That shape needs cancellation rules, partial result handling, and cost accounting for work already started. In either case, the join must surface disagreement, rather than average incompatible conclusions into false confidence. Parallel execution is not only a scheduling feature, it is a state-merging contract. The strongest design is often hybrid. Keep stable dependencies, permissions, budgets, checkpoints, and approval gates in the outer graph. Put open-ended investigation inside a node that can run its own loop. This preserves flexibility where the path must emerge and control where the organization already knows the rules. Use an explicit graph when dependencies and valid transitions are knowable, branches are genuinely independent, or failure must remain local. Prefer one loop when the work is mostly sequential. Every next step needs the full evolving context, or hard-coded stages repeatedly fight discovery. Explicit structure is valuable, but it is not free. It adds state merging, routing tests, duplicated context, and coordination overhead. Graph engineering is not the replacement for loop engineering. It is the discipline of making coordination explicit when implicit control is no longer sufficient. Loops remain the right primitive inside nodes and across exploratory work. Graphs add inspectable dependencies, decision ownership, durable state, bounded recovery, and branch semantics around them. Start with the simplest verified loop. Add graph structure only when the task exposes a real control boundary. The goal is not to draw more arrows. The goal is to make the necessary control visible, testable, and recoverable. If this video was useful, subscribe to Multi-Agent Academy and connect with me on LinkedIn. I'll keep publishing evidence-backed work on agentic systems. In video 2, we'll audit the graph engineering claims that went viral and ask what survives verification. I'll see you in the next one.